Okay, for this video, I'll be going through pure physics, pressure, success criteria D. Recall and apply the relationship density equals to mass over volume to new situations or to solve related problems. So this is the definition for density. It is defined as mass per unit volume. So every time you see a per, right, it means divide. So what is being divided by what? Basically, it is mass divided by volume. So this is the formula for density. Okay, now this is a symbol used for density. It is called rho. Okay, please do not pronounce it as P. Okay, so it's written like a P. It's written like P, but it looks like that. Okay, so if you are not comfortable, you can just use density equals to mass over volume. Okay, now the SI unit for density is kg per meter cube, and the SI unit for mass is kg, SI unit for volume is meter cube. Okay, so please take note, SI unit for density is kilograms per cubic meter. Density is a scalar quantity, so now you have one more scalar quantity if you need to quote examples of scalar. Okay, the common unit for density is grams per cubic meter. So we will need to know how to convert kg per meter cube to grams per cm cube and vice versa. Okay, however, take note, we will not have kg per cm cube in our syllabus or grams per meter cube. Okay, we try not to have these two weird combination. So usually it's just SI unit versus the non-SI unit of grams and cm cube. Okay, so density of common liquids such as water and mercury are 1000 kg per meter cube, okay, or 1 gram per cm cube, and 13,600 kg per meter cube, or 13.6 gram per cm cube. You do not need to memorize these values, but it will be useful if you know. Okay, so with this, I would like to use the water's density. Okay, if I'm converting from kg per meter cube to grams per cm cube, I will need to divide by 1000. Okay, that means if I want to go from grams per cm cube to kg per meter cube, I will have to multiply by 1000. Okay, so I suggest you just memorize one way. Okay, of course we have the math to prove it. Okay, the kg to grams you multiply by 1000. The meter cube to cm cube you multiply by 100 times 100 times 100, because there are meter cube 3 times of meters, you need to change it to cm. Okay, and as a result, this value over the larger value of 100 times 100 times 100 will in the end give you divide by 1000. Okay, so you can memorize it at the start from kg per meter cube to grams per cm cube. You divide by 1000. Okay, but as you get familiar with this density, I think it will come to you. Okay. Next, this is an experiment to determine the density of liquid. Basically, you have done it in lower sec, right? So to find the density, we actually need information about mass and volume. So we are actually measuring the volume, okay, using a measuring cylinder, and at the same time we put it on an electronic balance to get the mass. Okay, how about the density of a solid? Okay, if it can fit into a measuring cylinder, fine, we can just drop it into the water and then read the difference in the volume of water that was displaced or pushed up. And after that, you can measure the mass of the solid using the electronic balance. Okay, so density can be used to identify substances or the purity of substances. Density of pure gold is 19.3 grams per cm cube. Just for practice, it will be 19300 kg per meter cube. Okay, converting from grams per cm cube to kg per meter cube. Okay, and one thing to take note, if you have two fluids, one is low density, the other one is high density. Okay, in comparison, the low density will float, the high density will sink. Okay, now papers are sold in packets labeled 80 grams per meter square. A sheet of this paper of area 1 meter square has a mass of 80 grams. So the thickness of each sheet is 0.11 mm. So what's the density of this paper? So this question is tough in that they are using a lot of units. okay, not the SI unit. We do have SI unit, so this is the area. Okay, so they are labeled like that, okay, grams per meter square. They have a mass, okay, and the thickness, it is 0.11 mm. So they want us to find the density. Now density equals to mass over volume. That means I need to get information about the mass and the volume. Okay, so because we have the area, we have the thickness, we can actually find out the volume. So equals to area multiplied by the thickness, but the area is in meter square. Okay, so that's the difficult part. The thickness is in mm, but if we look at the options, it is in cm, right? So I need to convert my meter square to cm. So it's 1 meter square, so I need to multiply by 100 twice, because every time I multiply by 100, it is changing from meter to cm, and because it is meter square, I need to do this twice. Okay, and this is in cm. Now I need to convert the thickness into cm. Okay, 1 cm equals to 10 mm. Therefore 1 mm, it is 1 over 10 cm. So in order to convert mm to cm, I need to divide by 10. Okay, so it will be 0.011. So this will give me the unit of cm square. This will give me the unit of cm. So in the end, I will have the unit of cm cube. Okay. Okay, so if you press your calculator, you should get the volume as 110. Okay, so now we have our volume. We just need our mass, which is 80 grams. So 80 grams divided by 110 cm cube. Okay, make sure that the units tally. So 80 divided by 110, I get 0.727 grams per cm cube. That means it is answer is C. Okay, so the difficult part about this question is that the units you need some conversion. Okay, a cube of mass 5 kg, so this is m, with sides 2.2 meter long, has a cube of side 0.1 meter cut from its corner as shown. What is the density of the remaining portion? Now this is a trick question, because if the cube is of a uniform material, that means every part of it is the same, then the density will be the same regardless of whether it is one whole part or whether some part of it is cut off. Okay, so imagine I have this object. So if I cut it into half, right, this part will have the same density as this part. Okay, so even though this cube has some part of it being cut off, the density should be the same. So I can actually calculate the volume of this cube. So the volume, it is 0.2 times 0.2 times 0.2, because it is the uniform. Okay, so I get 0.008 meter cube. Okay, I also take note that the units used is in meters. Okay, then now I have the mass. Mass is 5 kg. Okay, so density equals to mass over volume. So it's 5 divided by 0.008. So it will be 625 kg per meter cube. Okay, so even though a part of it is cut out, but the mass and the volume decreases proportionately. Okay, therefore the density is the same as even though it is before cut out. Okay, 3 identical blocks of wood are floating in different liquid. A student makes the following statement: density of liquid X is the least among all 3 liquid. Density of X is less than the density of water. Density of liquid X is greater than the density of liquid Y. So which of the following statements are correct? So the wood is the same, okay, and we see that the wood actually floats the most in liquid Y. That means versus water and liquid X. That means the density of wood is only slightly higher. No, it's is much lower than liquid Y, because as you can see, the wood is floating so much higher in liquid Y, right? So the difference in density is there is a big difference in density. That's why the wood is floating so high. So I would say that Y has the highest density. Okay, and we see that for X, in liquid X, the wood is not floating very high, right? So X has the least density. Okay, lowest density. Okay, so water is in the middle. So the density of liquid X is the least among all three, true. Density of liquid X is less than the density, true. And density of liquid X is greater than the density, this is false. So 1 and 2 only, so answer is C. Okay. Okay, let me go through success criteria E as well. Okay, recall and apply the relationship pressure due to a liquid column equals to height of column times density of liquid times gravitational field strength to solve the problem. Okay, so before I go into that, we actually have covered contact pressure, whereby we are dealing mostly with solid, right? So the formula that we have touched on is pressure equals to force over area. Okay, and also even though we have hydraulic press which uses liquid, but it is still using the concept of contact pressure. Pressure equals to force over area. That is what I would like to think. For success criteria E, we are dealing with liquid pressure. Okay, so a liquid exerts pressure on the base of its container because of its weight. So the pressure exerted is given by the following equation. Pressure equals to rho GH. Okay, where pressure is where P is pressure, Pascal. Okay, rho is density of the liquid, kg per meter cube, and G is the gravitational field strength. So we this is actually a SI unit formula. Okay, whereas for the P equals to F over A may not need to be in SI unit. Okay, take for example, my force can be in Newton, my area can be in cm square, therefore my pressure will be in Newton per cm square. Okay, but if we have our unit for force as Newton, the area to be in meter square, then this will be Newton per meter square. We can call it Pascal, which is the SI unit for pressure. Okay, so it depends on what you are given. If the question wants you to find the pressure, the contact pressure in SI unit, then you absolutely need to express it in Pascal, which means the force must be in Newton, the area must be in meter square. But if they don't need you to find the pressure, the contact pressure in SI unit, which is Pascal, then you can leave it in Newton per cm square. Okay, but in this case, for this formula, P equals to H rho G, you actually have to have everything in SI unit. Okay, so usually for G, right, we'll keep it as Newton per kg. Okay, we will not tamper with this. The density we can give you in grams per cm cube, so you have to convert it to kg per meter cube, which means you need to multiply by 1000. Okay, if there's also a height, so I think I missed out the H. Okay, H is the height. Okay, so the height they can give you in mm, which is not SI unit. They can give you in cm, again not SI unit. They can give you in meter, so the meter is the SI unit. So you need to be able to convert your mm to meters or cm to meters if you want to use this formula. Okay, more about this equation. We observe that pressure of a liquid depends on its height and depth of the liquid. Okay, and the pressure of a liquid does not depend on the shape, size, cross-sectional area of the container. So this container or this vessel is called a communicating vessel. Okay, so you can see that the water will just fill up even if you pour the water in, it will just fill up, and it will in the end result in equal depth or equal height of the liquid. Okay, because pressure acts equally in all directions in a liquid, and pressure is a scalar quantity. Okay, so now you know density is a scalar quantity, pressure is also a scalar quantity. Okay, so let us try applying the formula. A diver is 20 meters below water surface, so I can call it the height of water above the diver. Given that the density of the water is 1000 kg per meter cube, so this is in SI unit, we don't need to convert. 20 meters is also SI unit, we do not need to convert. They want us to calculate the pressure P exerted by the water on the diver. So pressure equals to rho GH. We know our density is 1000, the G is 10, the height is 20, so you multiply together will be 200,000 Pascal. Because everything was in SI unit, we can leave the answer in SI unit, and for this formula, it's a SI unit formula. So you can leave it in 200,000 Pascal or 200 kilopascal. Okay. Next F. Describe how the height of a liquid column may be used to measure the atmospheric pressure. So now we are actually going into liquid pressure and gas pressure. Okay. Now what is atmospheric pressure? It's the pressure exerted by the weight of the layer of air or atmosphere enveloping the earth. This weight of air exerts a pressure on the surface of the earth and is about 10 to the power of 5 Pascal at sea level. Now, do you need to memorize that atmospheric pressure is 10 to the power of 5? You don't need to, but it is useful if you know. Okay, so the higher the altitude, the lower the atmospheric pressure, because the air above is thinner, is less dense, that the weight that they exert per unit area is lesser, so the atmospheric pressure is lesser. So atmospheric pressure is useful to us in many ways, like drinking water from a can using a straw. So we are not actually sucking up the liquid, we are actually sucking up the air and allowing the atmospheric pressure to push down on the liquid surface to push the liquid up into our mouth. Okay, and also allow us to breathe in air. Okay, so we use a simple mercury barometer. So that is why you need to I don't think you need to know, but it's good to know that the density of mercury is 13600 kg per meter cube. Okay, but mercury is actually poisonous, but it is one of the densest liquid. Okay, so last time they used to use mercury. Okay, it's used to measure atmospheric pressure. It's made using a glass tube about 1 meter long. Okay, so there is 0 Pascal in vacuum. What is in vacuum? Nothing. So it will not, okay, it's nothing in vacuum. So it will not exert a pressure on the liquid surface. Okay, but outside there is actually atmospheric pressure exerting on the mercury. Okay, so this atmospheric pressure is greater than the pressure due to vacuum, because there's basically no pressure exerted by vacuum, right? There's nothing in there, no gas or air. So the difference in pressure will lead to a resultant force. The difference in pressure results in a resultant force, and then it pushes the mercury up a certain height h in the tube. So the larger the difference in pressure, the larger the height h. So if I go to a place whereby comparing this diagram to this, right? If the height of the mercury that it rises up is lesser, okay, then that means the atmospheric pressure in this location is lower. Okay, so take note, the height is only affected by the change in atmospheric pressure, right? The density of the liquid and the gravitational field strength. Okay, the height is not affected by a change in diameter, right? As we can see from the communicating vessel, by tilting the tube or adding more mercury or a change in temperature. Okay, so let us see. An ideal mercury barometer are shown in the diagram below. They ask us to calculate the atmospheric pressure and what is the pressure at point X. Okay, so there are two steps that I need you to use when you are solving questions involving liquid pressure. Okay, so the first step that you need to know is draw downward arrows on liquid surface when there is air, gas, or atmospheric pressure acting on the surface. Okay, so I will demonstrate step 1 now. Basically, there is atmospheric pressure here. There is atmospheric pressure here. Okay, now how about inside here? They are telling me that it's an ideal mercury barometer. An ideal one means that it is a vacuum inside the tube. Okay, that means there is nothing inside, no air. So it's vacuum, so there's no pressure exerted on the liquid surface. So over here, I do not need to draw the downward arrow. Okay, step 2 that you need to do is you need to apply this concept called same liquid, same level, same pressure. Okay, so now we need to see where do we have the same liquid, same level, and same pressure. I can first of all identify this part, whereby at this height or at this point we have same liquid, same level, same pressure. So the pressure at this line that I drew, it is the same throughout. But this part where I chose is not useful in helping me to solve the question. Okay, so I would actually use this part here. Okay, we have the same liquid here, same liquid here, same liquid here, same liquid here, and they have the same, they are at the same level. Therefore, I'm proposing that they have the same pressure exerted. Okay, so if I were to take this point number 1, at point number 1, okay, the pressure on this liquid is due to PATM. Okay, and I'm going to talk about this point here being point number 2. Okay, point number 2 is the pressure at point number 2 is due to the height of liquid above it. It is this height of liquid above it. Yes, because the weight of this liquid column is acting on this point. So at point number 2, the pressure due to it is the height of liquid column above it. Okay, and if they are the same liquid, yes, they are at the same level, yes, that means their pressure is the same. That means the pressure at 1 is equals to pressure at 2, because same liquid, same level, same pressure. And the pressure at 1 is actually due to PATM. The pressure at 2 is due to the height of liquid above it, which we can calculate using rho GH, right? So they ask us to calculate what's the atmospheric pressure. It will be equal to the height of the liquid column inside, because we are applying same liquid, same level, same pressure. So the density of mercury, let's say I set it to be 13600 SI unit, G is 10, the height is 860, right? 860, because it is from here to here, right? Minus 120, right? That is the actual height. So it will be 860 minus 120. So let me do my calculation. Oh, but because this 860 minus 120 is in mm, so I need to convert it to SI unit of 1000 by dividing it by 1000. So 860 minus 120 divided by 1000 to change it to SI unit of 0.74 meters, multiplied by 10, and then multiplied by 1360, the density of the mercury. So I'll get 100,640 Pascal. Okay, so this is how we solve liquid pressure. So they ask us to calculate the pressure at point X. That's for part B. At part B, we actually have a height of 140 mm of liquid above it, right? So we can just find that pressure at X equals to rho GH, okay? So equals to 13600 multiplied by 10 multiplied by 140 over 1000. Okay, I'm converting my 140 mm to meters by dividing by 1000. So 0.14 times 10 times 13600 equals to 19,040 Pascal. Okay, so the pressure at X is lower than the pressure at point 2 because the amount of liquid acting at X is lesser. That means the weight of the liquid that is supporting is lesser than the weight of liquid at point 2. Okay, now to F2. The first diagram on the left shows a simple barometer in its original setup. Okay, it's a simple barometer, so we can take it that it is not faulty, so inside is vacuum. Okay, and the first step is that we will need to draw downward arrow to show that there's PATM acting on the liquid surface outside. Okay, and same liquid, same level, same pressure. So at this point, at this height, with this height of mercury, we will have the same pressure, right, due to that. So we will need to look for the height, okay, because it shows after some changes have been done to the setup, but the location is still the same, right? Which means that they only change the setup, but the place where they are conducting this experiment is the same. That means the atmospheric pressure should not change, right? So we are going to look for this height of mercury column, okay, whereby we have same liquid, same level, same pressure. So over here is also PATM, and we see that this height, okay, this height is actually lower than the height in, let's say, the first diagram. In the first diagram, it's actually lower. That means the atmospheric pressure is actually lower, okay? But because they are in the same location, atmospheric pressure should not change, so A is up. So for B, we see that the height is actually more, right? This HB is more than the height in the first diagram. That means the atmospheric pressure has increased. But again, they are at the same location, so atmospheric pressure is the same, so B is out. Now let's take a look at C. So although this part is lesser, but the height of the liquid column, it is same as the first diagram. Therefore, C is the answer because it will show that they have the same atmospheric pressure. And let's look at D. You check that the height is again higher. Okay, although mercury was removed, but by right, the height between the liquid level over here and inside should be the same. So this one actually shows that the P atmospheric is actually higher. Okay, so again, that can be the answer. So C is the answer. Okay, F3, a diver is 20 meters below water surface. So this is the height. Given that the density of water is 1000 kg per meter cube, so this is the water. Now, what is the amount of pressure exerted on the diver? So these questions look similar to the previous question whereby we were calculating pressure on the diver. So we are using this formula, but they are now asking for the amount of pressure. Okay, if you were to look back at the question here, they are just asking what is the amount of pressure exerted by the water. But now that we learn about atmospheric pressure, okay, so imagine the diver is over here. Okay, we have this height of 20 meters, and on top of here we actually have PATM, right? Remember, whenever PATM, step 1, whenever there is air, gas, or atmospheric pressure acting on a liquid surface, we draw a downward arrow so that we'll remember that the total pressure is due to the height of the liquid above the diver plus the PATM. So now we just need to add in 10 to the power of 5. Okay, so density is 1000 times 10 times 20. Okay, plus 10 to the power of 5, and your answer will just be this. Okay. Okay, a barometer was constructed using water instead of mercury because mercury is poisonous, but because the density of water is 1000 kg per meter cube, which is actually 13.6 times lower than mercury. So now they want us to calculate the height of water if the atmospheric pressure is 760 mmHg. Okay, so because the pressure of the ATM for both barometer is the same, right? So how do we calculate the height? So let's say this part is water and this part is we are using mercury. Okay, so the atmospheric pressure for mercury is 760 mmHg. Now let me explain 760 mmHg. So this 760 mm is obviously the height. This Hg will mean that what is the liquid, but what is the liquid characteristics that we are using? We are actually using the density. Okay, so we have our rho and H, but we are missing our G. Okay, so why is it that G is omitted over here as only as 760 mmHg, just the height and the density, or actually the chemical symbol for mercury? Is because we are all living on Earth, right? So there is no need to use the G. Okay, if I were to give a value of 500 mmHg, straight away people will understand that this pressure is lesser than the atmospheric pressure. Vice versa, on the other hand, if I say now we have 1200 mmHg, okay, you will know that this pressure is greater than atmospheric pressure of 760 mmHg. Okay, so this becomes a very convenient way of conveying what is the atmospheric pressure right now. So we don't actually need to press on our calculator, we don't need to consider the G, because the G is the same on Earth. Okay, so now we have 760 mmHg. Maybe we can write out what is the formula. It's actually rho GH, right? We have to use rho of mercury. G is the same, the height of mercury, right? So the density is 13600. We have our G, and the height is 760 mm over 1000, because we want to convert it into meters. On the other hand, if I'm doing for the water, it is again rho water, G, and H water. And H water is what we need to find, right? The height of water. So density of water is 1000. The G I leave it because I'm going to prove a point, and I have HW. So the atmospheric pressure is the same, but it's just that we are using different liquid to measure the difference in the height, to get the difference in height so that we know what is the atmospheric pressure. Okay, so my point here is that as G and G both appears, I can cancel them out. Okay, and with this I can then work out my height to be okay, 10.336 meters, right? Because I'm using everything in SI unit, so height will be 10.336. If you remember, if I use a simple barometer that uses mercury, the height is 0.76 meters. Okay, around there. That means for water, I will actually need to use a height, a length of a glass tube that is 10 meters, and that is very inconvenient. Okay. Okay, so I will continue with F5. Okay. Okay, water of density 1000 kg per meter cube fills up to a height of 20 cm in a vase. Okay, the base of the vase is broken, and water starts to leak from a tiny hole of 1 mm square. Okay, so this hole, the area is 1 mm square. Okay, to prevent water from leaking out, a sticky tape is used to cover the tiny hole. So what's the minimum force, F, that acts on the tape? Okay, so why does force come in? Because pressure equals to force over area. Okay, and they say take atmospheric pressure to be 10 meters of water. So 10 meters of water, it's very familiar. It's like what we did just now. Just now our height is about 10 meters as well, right? If you are using water, so it is consistent. So this is density of water. The height is 20 cm, so I can actually convert it into 0.2 meters, right? SI unit. Okay, so now first step, we need to draw arrows on the surfaces when there's pressure acting on it. So this is PATM. Okay, and the thing here is when we are talking about stopping the leak, right? Stopping the leak, we use a sticky tape, and if we lift up, there is actually atmospheric pressure acting on the bottom as well. And because on both sides, okay, if I'm talking about the pressure acting on the top of this tape, the top of the tape, okay, we actually have PATM plus height of liquid, okay, rho GH, okay, which is actually this amount of height of liquid. But if I am talking about the bottom, we also have PATM plus a certain force, right, that the sticky tape is placed on to prevent the water from leaking out. So this is the top part and this is the bottom part, okay, and we are trying to find the force, right? So the pressure is the same because the tape remains there, okay? So at the bottom of the tape we have PATM plus the pressure, okay, so which is actually equals to force over area. So since PATM appears on both sides, they can be cancelled out. So I just need to find the pressure on the top of the liquid, sorry, on the top of the tape due to the liquid, and it will be equals to the force exerted by the sticky tape to prevent water from leaking out. Okay, so substitute height as 0.2, density is 1000, and G to be 10. Okay, it will be equals to force over area. All right, so the area is 1 mm square. 1 mm square, I need to convert to SI unit, okay, because over here is already in Pascal, everything in SI unit. So 1 mm square is equals to how much in meter square? I need to divide by 1000 and divide by 1000. Okay, so basically, maybe I do my calculation. Okay, so I've calculated the pressure due to water is about 2000 Pascal. Okay, now I need to multiply by the area. So the area is 1 m square, so I need to convert it to meter cube. So I need to divide by 1000 2 times. And if I bring it over, it becomes 2000 times 1 over 1000 times 1000. Okay, so basically my F is now a value of 0.0020 Newton. Okay.